This is a physicist. He knows nothing about colors, but he can do integrals. Welcome.
Hello children. Today we're going to be finding the normalization constant for a one-dimensional Maxwellian distribution that should be squared. Oops. So for something to be normalized we would have this property here, and so we're going to have to basically just do the integral to find our constant a. That's our normalization constant here. You probably couldn't see that arrow. So this is actually a pretty tricky integral to do, so we're going to use one of our little nifty mathematical things, and instead of finding the integral, we're actually going to find the integral squared. Yes. And so to do this we then get two limits of integration basically, because we can't just use x twice. We have to put in a new variable y as a dummy variable, otherwise we will end up with, well, the wrong thing basically. So we get a squared exponential negative m on 2kt x squared plus y squared bracket. That's dx dy because we have to integrate over both of those. And so some of you may recognize this thing, oops, as being, polar coordinates basically. So we can reparameterize this. We can set r squared equal to x squared plus y squared. And we can take our dx and it'll go to r dr, and we're going to be integrating now over r in polar coordinates between 0 and infinity instead of negative infinity and positive infinity. That's just how they work. And then dy is between 0 and 2 pi, and it'll be d phi. Sorry guys. Alright, so who knows how to go from here? Yeah, let's dive into it. And so we take our integral squared and we get the integral between 0 and 2 pi, integral between 0 and infinity, keep our a squared, and we now just have something a little bit easier to look at. Negative m on 2kt, that's an m, times r squared. d dr, d phi. And so our phi integral is pretty easy to compute because it's just integral 2 pi over d phi, and so you just get 2 pi from that. The exponential integral is still a bit more tricky, so we're going to apply one more little substitution to make it slightly easier. And that is simply just setting over here, I'll do it. We set s equal to negative r squared, and so our dr, our rdr, should now become, our ds rather, should now become negative 2r dr. And so putting that down here, we get 2 pi times the integral 0 infinity a squared. Because we've set this negative 2r, we need a minus half here, and then just our exponential again, negative m on 2kt, just s now, and this is all ds. Next, just to get rid of this negative sign, we can swap our limits of integration, because I think it's an even function. I think that's a property we're using. Negative infinity to 0, so we swap it around, and then we get this negative sign goes away, so we just get, oh, that should cancel with that half anyway. No, I've screwed it up. There. A squared exp negative m on 2kt s ds. And now this is actually pretty easy to integrate. And so finally what we end up with down here is a squared, pi a squared 2kt on m. There should be a negative, shouldn't there? Should there be a negative?
No.
No? You sure? No, yes, that's right, because that negative shouldn't be there. Yeah. Yeah, yes. That's right. And then this is all times e to the 0, so plugging in for that limit there, minus e to the negative infinity. And so this here, that's just 0. Anything to the negative infinity is always going to be 0. E to the 0, that's just 1. And so finally we end up with that our integral squared equals 2 pi a squared kt on m. And so we want to find a, so firstly we got to go back to our original thing here. We know that that's what the integral equals. So we have that I equals root 2 pi kt on m times a, and that is equal to 1. And so we can just rearrange this and solve it for a, and so we finally get that a equals root m on 2 pi kt. And that's the integral, guys. So that's our normalization constant for a Maxwellian distribution in one dimension. Thank you, guys, and have fun.